So this is the cover of the book. We are trying to start the textbook 2, number 2, Elements of Ocean Engineering. And this is a chapter names: Ocean Environment, Offshore Structure, Coastal Process. Materials again, corrosion, and floating submerged body dynamics, underwater system, underwater acoustics, instrumentation for ocean, and physical modeling, and safety and ethics and design. There's the chapter names. We will cover not all of them. Right? Field development, offshore. Offshore is the other opposite word of onshore. Right? Onshore. Onshore is land side, right? Land side. Offshore is far away from the shore line, coastal line. So it can be a deep water. We are developing oil and gas field. And because of the onshore gas and oil, you can think about Gulf of Mexico. There has been many oil reservoirs inside the Texas land side, but that is exhausted because of more pumping. Now they are going into the water, one step by one step, from shallow water to the, now they are going up to the deep water in Gulf of Mexico. And why? Because there are many more oil and gas, 20 times of oil comparable to land side. But it is more costly, right? 20 times more cost to pumping up the oil from the sea. You need special devices, and far away, nobody wants to stay there. And so that many people are saying the oil price near around $60 is a threshold for developing offshore oil and gas. But now the oil price is down under the 60. And also the technology is developing. So more survey, more exploration, more production technology is coming. One of the examples is shale gas, but that is coming from land side nowadays. But in the future, it comes again to the seaside or again, right? But nowadays, there is enough shale gas in the land side. We are starting from land side. Anyway, that is coming from new technology, cheaper technology to extract oil coming from shale. That is, I captured yesterday night. That counts for different time zones. Anyway, CST time zone, Central Time Zone. So you can see that oil price is fluctuating up to around 55 in April, early April, but now comes down again to 50, right? So it's not enough for developing ocean plant. We need more price rise. Not so. Still, there is a problem for developing offshore plant in these days because of the low price of oil. And these are showing a reserve in the land side only, right? No ocean side, because we don't know yet how much oil and gas is buried under the seabed. So you see that there is only land side reservoirs, deposits. There are some. This is probably South Pole. or North Pole? North Pole, right? Is it North Pole? This picture? North Pole. So around North Pole there is many. Right? And this is typical structure of oil development, offshore field development. There is oil coming from subsea wells. There is a position of wells, small wells, typical small wells. And there is a gathering together. These small oil wells are gathering oil and gas here. And then it comes to the long distance to the riser or pipelines up to the offshore structures. And then above the water level, there is a processing unit. So this offshore structure can be fixed type or floating type. But anyway, there is a big structure there. So we are trying to learn about the offshore structures. How can we use this? And drilling is the exploration, part of exploration. Right? We need to drill first to see whether there is enough oil there. And drilling and production is two big steps. So exploration first, and then when we found a good enough reservoir, then we can start production. And for the drilling and production, we need such a drilling platform. So there is a surface platform structure above the water, and drill pipes, and blowout preventer. BOP is here, right? BOP location. Two sides. One is at the well side, the sea bottom side, where the water and land is meeting. So top of the oil well, and also bottom of the structure. There can be more, but usually they are blowout preventers. Something is coming with explosive or high pressure shock wave is coming. They shut down that kind of blows. And drilling flood with mud together. They are mixing somewhere here. There is a winch. There is a mud processing unit. So mud to drill and return to tank by a shaker and cyclonic filters. So they are coming into the here and then goes again. And drilling fluid with mud and casing and riser. This is casing and riser. You will see the video. And drill bit, the point pin that is rotating and grinding. So we'll see that one offshore drilling video. No sound. Anyway. 똑같아. 어떻게 한다 그랬지? 부끄러워야 한다 그랬나? So drill bit is drilling at the sea bottom. There's so you need some fluid with mud. It's coming together to make as a lubricant, working as a lubricant, and then pipe is coming to make more stronger well side pipe riser, or so that, and then more some caps is located to protect them. several times. And also there are there is some gaps between land side and also pipe, so they can be filled with some material, mud or cementing something. And next time they come to again, so drill is continued together. This is a separation line from water side and also deep down into the seabed. And then there is a more pipe is coming, a little bit smaller, and then continues into this. And then this is one case of blowout preventer, or we can call this is Christmas tree. That kind of thing is located at the bottom side to protect any some high pressure shocks is coming. And drill bit is also coming again to further drilling out to more depths into the sea bottom. And you see that some remainders, the rocks and soils are coming back into the upper side together with the mud and fluid so that it can drill continues together. So some depths you stop and then put pipes again and also filling the outside with mud or cement. Right? That because there is a gap here. Right? This one is filled. That is a typical way of doing continuing drilling up to 1,000 meters, right? More than 1,000 meters, up to their reservoirs, hopefully, finding oils and gas. Okay. So there is a measurement coming, the signals coming from the sound measuring, something like sonar. They are sending signals and returning back, so they record so that they can understand what is the composite of materials there. So they can expect how much further they should drill deeper inside, or they can decide to stop. Right? Sometimes, many times they stop. Okay, this looks like a shale gas drill system, okay, the pipe showing. All right, can continue to our slides again. Right.
The fluid they used to drill, is it the seawater or is it another fluid?
Mixing seawater with some material together.
Okay.
They are processing up here. There is some box or machine. This is a machine, a mixing machine, or filtering out, because there is mud is also coming backward, right? And so they processing, filtering out some big pieces, right? And then water is used again. And if you need more mud, then put more mud into
to cool the drill.
Cooling and something like a lubrication. Lubrication, yeah, something like a lubrication.
And then they pour like cement, concrete, and like they pour to like certain.
Right. So one first work is to make a lubrication when the drilling is doing, and so that they pumping out the other debris. The second time they put some cement in between gaps, pipe and land side. And types, there are different types. And also, again, two groups. One is for drilling, second is for production. So drilling system also, but the type is very similar, drilling or production, by how to make a platform. Right? So jack-up type, semi-submersible, and drill ships. So jack-up type usually has a putting onto the seabed, same as landside building. So it's only for shallow water. And drill ship is for deep water. That is only floating type. Semi-submersible is in between, but is almost floating type. A different style of. But nowadays, more and more deeper site is developing, so they prefer to build a drill ship. That is the trend nowadays. And also, again, for the production, again, they are also jack-up type too. And gravity structure is a little bit different, but basic idea is same. And floating types, there is a semi-submersible ship type is also do, but there is a different types like TLP and guide tower, and single anchor leg mode system, and FPSO. FPSO is very similar to ship, but the ship for production, this is ship for drill ship. And Korean shipbuilders are majoring in drill ship and FPSO nowadays. And spark platform is very similar to TLP. You see the structures in picture here. So tower is jack-up type. Tower or jack-up style. So they have a putting into the seabed, very similar to buildings. Right? For high-rise building, what is the problem? The wind power. Because it's a long beam, right? Long beam with one fixed arm. So there is a bending forces. There is weak on this long beam, right? Because it is fixed and on the bottom. But this one is more difficult because water force is higher than wind force. So that you need to have you cannot make a long structures there. TLP is a tension leg platform. You have a very strong, how can I say, mooring line. We call this tether, so that this has a very big tension. So it's almost like a structure, but it is all tension. This is a compression, right? But this is a tension. So that this one is have a floating buoyancy more than structural weight, so that tension is coming from grabbing from the root, so anchoring, and also floating power from the buoyancy. So tension is going on. So TLP, SPA is just floating one. SPA is floating. So you need some small mooring lines. And submersible also, semi-submersible is similar to floating. So from here, we see that this is floating type. But now they see that FPSO or drill ship type 1 is popular nowadays. This is for deepest one. They have a smaller number of mooring lines, so that they need to have a dynamic positioning system. Technology is developed. This is onshore fixed platform, and you can see that pipeline is coming from wells, oil wells, and not far from the land side you can use a pipeline. But if far away, you need to have a pipeline into the offshore structures. And the worldwide, but it is about 8 years ago, number of structures, fixed platform is many. Right? This is for short, shallow waters. But nowadays FPSO is increasing. So that is a new type of deep water. And water depth. You can see the water depth increasing. So this is deep water used for floating type. But more numbers in ship type, because this is easy to construct, because sometimes they can convert old oil tankers, convert into FPSO, because they can be ship-shaped. They also have pumps and pipes on the ship for the storage. So you need to only have a drill part. Drill part is needed. That's why they have a more jack-up rig. They have a long leg or footing that can be raised when they have a traveling, moving into the site, from the construction site to the production site, or they floating and moved down to with the leg is raised. When they located into the site, then they have an elevator type motion to legging down into the sea. And until then, there is a footing is arrived at to the seabed. So they can be used only relatively shallow water up to say around 120 meters. Still is long, right? Still deep. Fixed platform, the jacket gravity platform is something like this one. This one is special for Norway, I heard. And it was built a long time ago, but that was the only once, I guess. It is made of concrete, rather than this is still made, concrete type. And they have a very heavy tanks and gravity type, so that they submerge down into the seabed up to here, right? So that they stay there, something like a big structure, concrete structure. Built on concrete or steel legs and anchored directly onto the seabed, supporting a deck. Deck should be above water, right? Should be above water. Above water here. Designed for very long term use, because moving is not easy for them. To stay there, they may be abandoned there. Typical installation up to 500, but less than. And tension leg platform, TLP, we call this is tethers or tendons. The lines, this line, strong lines. And they holding so it's a tensioning, so that this buoyancy is higher than the weight of this one. So there's a more buoyancy, but this one is holding down, so that they have a tension, so that they do not move. Especially the heaving, there is not so much heaving. Even though there is a wave, known to be economical between depths around 1,000 meters. So there is a little vertical motion because of the high tension there, because of large tensile force from in tethers. Installation depth is around. Yeah. So above water, you cannot see whether this is TLP or same submersible. Under the water, you see. So anchoring is very important, because you need to have a strong hold. Right? And semi-submersible is floating type. Looks like this one. Is it semi-submersible? They do not shown us any platform. No, I don't know. There is a drill ship over there, coming from Samsung, maybe. Drill ship. But this submersible located in Sakhalin in Russia, but they do not see whether this is platform or submersible. Well, it looks like a submersible for me. But anyway, this is a floating type. Buoyancy from ballasted watertight pontoons. Pontoons is this one. The gray part, bottom gray part is pontoon. They make a buoyancy for supporting this platform, superstructure. and deeply submerged hull. Deeply means looks like not deep, right? The draft is more than wavelength. They are saying submerged hull or pontoons, or enhancing stability and reducing wave-induced loading. That is important because the supporting structure, vertical supporting structure, has a smaller water plane area, so that wave effect is smaller. Very similar to SWAT ship. Did I explain you about SWAT ship? SWAT. Did I explain you about this one? Small water plane area twin-hull ship. Twin-hull ship. The twin-hull ship, but small water plane area, so that the wave effect is smaller. Same idea, so that the vertical column has smaller area, diameter, so that reducing wave-induced forces. But this is good, but bad thing is this is sensitive to load changes. When something is loading onto the more weight, then change of draft is bigger. 10 ton or 100 ton is added, because water plane area is smaller, change of draft is higher. So it's sensitive to load changes. And also, you need to have a stability problem. When something is going on, and stability is something like spring back forces, right? Stability forces, restoring forces. But spring is smaller, so that it is not easy to maintain stability. When something is happening, say some cracks is happening, so that water is coming into there, then it can be trimmed, but stability can be lost. Anchored by chains and ropes, so you need to have a dynamic position. Every floating type, high depths, you need to have a dynamic positioning system. FPSO. This is a good business for. It was good business for Korean shipyard. It's ship-shaped one. Floating vessel for processing and storage. So FPSO is a floating, production, storage, and offloading. Offloading is for this is a shuttle tanker. So when the FPSO is full of oil or gas, then shuttle tanker is coming. So offloading is unloading oil and gas to the shuttle tanker. We call this offloading. Processing. So you need to have a processing raw material coming from the seabed, and simple processing, and then storage there. Okay, and particularly effective in remote area, deep water. Very similar thing, right? And pipelines up to land side is not costly because of far away distance. Near shore, you can use pipeline rather than shuttle tankers. It is more economical. And then it is a ship-shaped. It can use move relocation, and reservoir is empty. And spot platform is not many, but it is special. Floating type is very similar to TLP, but do not have so strong tension. Consisting of a large diameter single vertical cylinder. So the spar means big cylinder underwater. Big cylinder underwater is spar. And deck typically used in very deep water. World's deepest platform in Gulf of Mexico is 2,500 meter. One interesting portion of that SPA is some how can I say, the rounding staircase, something looks like a staircase in the SPA type. There is a line along the cylinder, right? That is to reduce motion, to make resistance on motion. And also sometimes they, because of the tidal motion, create vibration or motion. So they can be specially designed to reduce that kind of hydrodynamic forces. Design consideration. So the natural frequency of the motion, heaving, or other 6 degrees of freedom should be off the. So some design can be above the period of big high frequency waves, or lower than or upper. So you need to avoid the resonance of motions. Concept, design wave concept. In old days, we have a worst case designs, so higher design, largest wave coming during, say, 100 years. So it can be a very big, that we call this the worst case scenario. So nowadays, they changed to more stochastic ones. So probability of failure can be less than 0.01% something. So that can be the change nowadays. But in old days, there is not so much of stochastic or data set. We use worst case designs. So designing against structural failure due to largest waves. But also there is a problem for particular failure for many times of small size waves. So when you use 100 years worst case period for, this is API, is American Petroleum Institute. They produced the kind of table. So Gulf of Mexico, 100 years, maximum wave height in feet, wave period, 1 hour wind at the wind speed. This is wind speed. And each region of California, Oregon, Alaska. That can be used for your design. Right? Wave forces, how can you calculate wave forces? Different approaches. Important parameters is diameter, wavelength, wave height, and some non-dimensional numbers, something like a Klugen-Carpenter number. It is water velocity, and wave period, and also diameter, right? Diameter, period, and velocity. So the non-dimensionalized number, Klugen and Carpenter numbers. So this is guide for wave load calculation procedures. When diameter and wavelength is smaller or larger, right? And they use in big water, big wave, Morrison equation will be used, right? No, should not be used for computing wave forces. When there is is larger than wavelength is big, right? Big. No. Short. Wavelength is short. Because it's a dividend. So this is short waves, right? This is long waves. Wavelength is 5 times of diameter. More than 5 times of diameter of the pipe. Not pipe, the cylinder of the structure. Right? More than 5 times of the wavelength is more than 5 times of. Then you can use Morrison equation. We'll see that Morrison equation. And Klugen, Carpenter numbers, Reynolds numbers, and inertial coefficient and drag coefficient, peak velocity of water, wave period, kinematic viscosity, and diameter. And then Klugen Carpenter number is above. Above means high speed of water, and period on diameter, and in middle range and low range. So in high speed, big or long waves, then it can be a drag dominant, and this time is inertial dominant range. So different approaches should be used. So it comes with a Morrison equation, or differential form that is divided into inertial force and drag forces. Wave fluid acceleration for inertial forces, and velocity for drag forces. Total wave forces calculated based on volume of the member element and projected area of the member element and drag and coefficient. So anyway, there is a equation you can use for a wave load calculation. And design wave is coming from 100 years of frequency that is coming from table. Right? No question. You can continue.
So from calculating wave forces, I continue the lecture. So when you make the structure, we should consider some forces. So one of them is wave force. So wave force, we should consider the wave-induced force, like of the offshore platform, because of some seawater, and in that procedure we can use Morrison equation, and Morrison equation is as we saw before, like this, and you can see this picture. When you think about the pipes underwater, we should consider the forces of pipes, and there are forces caused by waves, and we should consider the horizontal force and vertical forces and control to be balanced. And so we'll check the wave theory to use this idea. The linear wave theory or airy wave theory is the theory linearizing the waves to calculate easily. So let's assume there's a wave like this picture, and we can easily make sense, get to know these components. So this equation, the surface free surface elevation. So we can use some differential equation. So we can express that as some cosine or sinusoidal function, and we can get solution like this. So the frequency can be expressed like this, omega. And this is a real example of wave force. So we can use wave theory to analyze the wave force. So this picture shows some wave period, a single wave period. And let's figure out the factors related to the wave forces. First, we will see some variation of drag coefficient with Reynolds number, and we arrange in order of roughness. So, this, and as we saw before slide, there was a non-dimensional number, Krigan-Carpenter number. So this number. What is the Kriegel capital number? This explains the relative importance of the drag forces over inertial force of blow objects in an oscillatory fluid flow. So when there is a small Kriegel Carpenter number, the inertial force dominates, and large Kriegel Carpenter number, the drag force dominates. And this picture shows the inertial coefficient with Reynolds number and Kriegel Carpenter number. This is some drag coefficient with Reynolds number and Kriegel Carpenter number. So here's an example problem. The example of jacket structure. Dimensions are given and you can utilize them to solve the problem. So dimension of depth or that one, or wave height and some wave height and period. So we can refer to this picture. So this is wave height and sea level. This much is depth. So we can figure out inertia and drag and total force in this picture. Until now, we consider the vertical cylinder structure, and from now we will consider the horizontal cylinder. That will be a little different from the vertical cylinder. When you thought about the case of vertical cylinder, we only treat the wave force. But in this case, we also consider the not only wave force but also some current force. When you think about the vertical cylinder, the current force was neglected because it was very small, and we will consider now both of them. So wind force and current forces are evaluated by above equation, very similar, and there are some density, drag coefficient, area, and velocity. So this picture shows some drag coefficient as a function of Reynolds number in the steady flow. And wind speed. First one is sustained wind speed. The sustained wind speed is some consistent wind, consistently blowing wind, and we can get the speed, the average wind speed for time 1 minute at an elevation of 10 meter. And gust wind speed is instant speed in not consistent wind, so blowing in one time. So when you get the gust wind speed, average wind speed measured over a time of 3 seconds, very short time, short duration, and elevation of 10 meter. This is subsea system. We will from now we will figure out this terminology, wellhead or jumper manifold or something like that. So first, wellhead, also called Christmas tree. Wellhead is an operation system for drilling oil. It is also called Christmas tree because they look like some Christmas tree. There are many valves on the wellheads, and they look like Christmas tree, so we call we also call them Christmas tree. And manifold is something gathering productions or valves from the multiple wellhead. And there are also control system, something called SCM or UTA, and connection system like PLET. As we all know, offshore pipelines, there are many pipelines. Some of them are buried, or some of them are beneath on the seafloor. And we can also see some two terminology: flow lines and pipelines. Flow lines are some also called production lines or import lines, and pipeline also called export lines. There are some differences between them. So flow lines are used usually to transport unprocessed fluid or multi-phase fluid, or deep water flow lines may carry some. There are merits, like they can transport some very high pressure or high temperature fluid, and the pipelines are used to transport processed oil or gases, and single phase and generally greater size. So this is picture of this long one is pipeline, and this short one is a flow line. And also here is some midship section of flow lines. This is a real picture of pipeline. Also, we should consider the forces when pipelines are in the water. So forces by wave and current should be expected. So the x-axis and y-axis. So this is some relation of table. So according to the Reynolds number, the drag coefficients or lift coefficients, inertial coefficients, we can see some. And marine pile foundation. Marine pile foundation is something like we first see some video. This is marine pipe driving. It is drilling. And installing some template. Very slowly pile driving. Driving pile very carefully. Yeah. So marine pile foundation is some for soft sediments in hot bottom areas, as we see the video. seafloor can support gravity foundation. So when we are driving piles with large, we use large impact hammers, as you can see, and some drilled and grouted piles for open hole. Yeah, and hole is drilled and pile is lowered into the hole, as we saw the video. So, and the above things are some parameters, or when we consider the hydraulic. And there are two categories of foundations. First one is fixed platforms. First one is gravitation, driven pile, drilled shaft, and suction caisson. And next one is a floating platform, drag anchor, plate anchor, suction pile, suction embedded plate anchor, etc. Suction pile is installed by applying suction pressure inside the pile, and we push the pile into the seafloor. So when we install this one, it should be economical and environmentally friendly, because we push them in the seafloor. And the merit of this one is fast installation and removal, and it can be applied to large structure at deep water. Finally, this is suction pile installation. Thank you. Is there any question? Thank you.
And I will start discussion. In this class, we will learn about offshore structures related with resource like gas and oil. Then in other industry like laser, there are also offshore structures used. This is the world's wonderful restaurant, but their restaurant is not located in deep water, just under 5 meters below the sea. Then, how about living industry? This is the one of blueprint of underwater city of Japan. The first floating area is that sphere is the floating undersea, and that radius is 500 meters, and that sphere exists in the sphere. In the spire there exists the residence and the business place, and the head is maybe 4,000 meters. Then how much does it cost? How much does it cost to build? Anybody guess? Right?
For room or for house?
That whole structure, yeah. That they announced that $55 billion. That Korean money is that I don't know. Then this is my question. It is necessary to live on the ocean despite that spend many resources and money.
Anyway, it may be cheaper than going out to space if we are running out of land. So it may necessary.
Yeah.
Depends on the condition. Future or
Any other ideas? Yeah.
I think focusing on the energy efficiency, in case of the very high altitude, high building, there's they have not good energy efficiency, so that just the top of the buildings. So for the case of the ocean, if the water is more good transmissivity on the thermal transmissivity, so it is not the focusing for the focusing on the energy efficiency, it is not a good place to live. So
You mean
you have to live in the water.
yeah? You mean the build on the high building is more difficult than
No, like the high building, the wind make the low efficiency of the
yeah, really.
fully
And any ideas?
I don't think that is necessary, and especially there will be some problem for the human to live underground under the water. I mean, I don't know if it's possible to live without seeing the sun, the sky. Could be some mental problem for the people who live there.
Yes. Good ideas. Yeah, you first.
I think the only way it could happen is if you have a very incredibly densely populated area like Hong Kong or Singapore or something like that, and if they want to expand to accommodate for more people, they have no more room on land, which they could not have anymore in the distant future. So then maybe I think it could be necessary to live on the ocean or on the moon.
Yeah. And our next question. You are talking about this before question like this. we can think about people because of people have the long life and because of environmental pollution. So in the near future, there are lack of residence place for living in the ground. So there are these three places that replacement, like outer space or ocean and underground. So what is the best place to replace the landing for living? Affect safety or view or this? Yeah.
I think since the water is like the most important kind of thing we must save for live, I think that ocean may be like a good idea with like kind of treating system for like seawaters, and we can think of I don't know, underwater seaweed farming, for example. But like this is really unlikely to happen like in the far future, the next few years at least, I hope. But yeah, like Paul said, I think there's like problems with mental disease, like craziness. Like maybe if you're born in it, if you spend all your life in it, maybe it's possible to live. Actually, that's what is promoted in some movies. I don't know.
Is there any idea about underground is best? No? Then raise your hand on about ocean is best. Raise your hand. Then space, out of space best. And what is the reason? Why you think space is better?
I don't know the related living condition, where is the better place, but I think that space is the most nowadays funding place. You know, those futuristic guys, they always make an investment in the space. So that's why I think it will be the best place to replace the land for living.
Just to be clear, you think about space or another planet?
Yeah.
If you stay in the void, it's obviously not the best place. But yeah, maybe like going on Mars, like there's a mission of living on Mars. I don't know where it is now, where the process is now, but I think it's still going, and people are getting ready to one ticket for Mars and no coming back. Why not? Some people are studying it.
Many have one idea. Then my discussion not finished.
Underground. I guess the cost for construction may be minimum for underground city. Underground. underwater is tricky. Underwater.
Yeah, but you have to be lucky where you be your city, and it's usually not that much volume for a full city. And yeah, it can be dangerous. I mean, every underground city can be dangerous. And the ocean too. There's earthquake or something.
Earthquake can damage any. So underwater is more safer to an earthquake because there's no direct contact to the. There's a shock observing by the enemy. There's a floating, but the shock is not direct to the.
I mean, you can imagine oxygen pumping from water. Like underwater, there could be very many possibilities around. Except Mars.
All right, I can see you on Sunday.